So, good afternoon, everybody. Welcome to the first PCCL webinar. My name is Gernot Oreski. I'm Division Manager at Polymer Competence Center Leoben, and I have the honor to moderate this session for today. So, as I said, this is our first webinar, and we plan to continue this webinar series in the future. So that means every 2 months you can expect a webinar with some of my colleagues telling you results, showing you success stories, showing our capabilities, and showing actually the research that we do. The first speaker is a colleague of mine, also division manager for the Elastomer Technology and Process Optimization division. It's Bernd Schrittesser. So he is a polymer engineer from Montana Universität Leoben, and his specialty are, let's say, R&D on elastomers. And today he will show us results on his R&D projects that he had for elastomers for harsh environmental utilization. So Bernd, thanks for having the first webinar and for taking over now.
Thank you very much, Gernot. Also, thank you very much for a kind of introduction. As already mentioned by Gernot, we'll give you today a short overview about the activities in the field of elastomers, what we have in our industry and also in our strategic projects at the PCCL. Before I start with the focus on the elastomers and also on the harsh environments, I will start with a short overview about the PCCL, so only 3 to 4 slides. And here we are. So what is the Polymer Competence Center Leoben? It's more or less the leading Austrian center of excellence for application-oriented research in the field of polymer technology and polymer science. Our foundation was 2002, roughly turnover of 12 million euros and employees roughly 125. Concerning our ownership structure, as you see also here, we have no company in our ownership structure, so we are only owned by research institutes and 5% also by the city of Leoben. What we're doing so far, or what is our main goal? Our main goal is that we'd like to focus with our research program on the value chain, and we also try always to start from the chemistry, went over processing, to characterization methods, also to simulation of polymer components, ending up with industrial applications. This is the way we're doing research here, to finally understand what's happening with the material in the different applications. More or less what we offer you is long-term R&D projects with industry partners and also with additional scientific partners. We give you the possibility also to access easily public funding schemes, for example, the COMMIT program in Austria. But nevertheless, we're also working on contractual basis and also give you the possibility of some material characterization analysis or simulation, what we have in-house in terms of service. To give you an overview, as Gernot mentioned, we have different divisions at the PCCL focusing on different topics. Here, first of all, as also I've showed you for the value chain, we'll start with chemistry of functional polymers. Then we have smart material surface testing, polymers, composites for structural applications, simulation and modeling, and the division I'm heading, elastomer technologies and process optimization. And today, I'd like to give you a little bit more detail about this division. So at the end, or overall, we are 3 research groups in the division. So we have polymer tribology, headed by Dr. Hausberger. We have processing technologies, headed by Dr. Kerschbaumer. And I'm also heading, additionally to the division, the research group, material science and testing. And here on the side, you see a short overview. As also Gernot Oreski already mentioned, I studied polymer engineering at the Montana Universität Leoben, joined 2010 as a project lead at the PCCL, 2014, then worked on as a group leader, 2017 as a division manager, and with 2020 we received also additional fund for a commit module, where I'm also additionally heading this commit module as executive manager. The scientific focus basically is more or less in the field of soft materials. And here I'm focusing on material characterization, fatigue, fracture mechanics, aging, long-term behavior, material selection, filler strategies, mud materials, and also materials for harsh environmental utilization, as I will also explain today a little bit more in detail. Good. When we are talking about harsh environments and when we are thinking of elastomers, then when we think a little bit of different applications, we find elastomers all over the different fields of applications. For example, oil and gas industry, automotive tires, air also tires, some hoses or some seals, space applications, food industry, plant engineering, just to give you a little bit of examples. And today it's not possible to talk into detail about all of these application fields, but I'd like to start with oil and gas industry and give you just a short overview where elastomers are applied there. And as I've already mentioned, seals are very important when you think of safety of such oil rigs. For example, here the blowout preventer. Here we have hydraulic seals, we have seat seals. When you think of the production of hoses, of mud hoses, then you have these flexible hoses. When you think of some Christmas trees, where you have some valves or some connectors, then you need also seals, FS seals, T seals, and for sure you also like to drill a hole. Yeah, you also have a drill bit, and the drill bit also have seals. More or less here we have these different applications and what it brings together or what it has together, these different applications. We have a variety of influencing factors on the material. So when we are thinking of application at very low temperature, for example, Arctic climate, we have temperatures down to -40. When we think of very high temperatures, drilling depths up to 10 kilometers, for example, or high temperature reservoirs, then we have temperatures up to 200 degrees. Pressures up to 1000 bar in combination with very aggressive media. And all of this leads to an impact on the material performance, on the long-term performance. So we will receive, for our material and application aging, we will receive swelling when we apply oil, gases. And what we are doing here at the PCCL and together with our company partners in different research projects is we try to get inside what's happening with the material in the application. And therefore we are utilizing different classical testing devices or classical testing characterization techniques. We're doing creep relaxation, dynamic mechanical analysis, fatigue fracture, applying high-rate fracture tests, and also end up with some specialties like the rapid gas decompression behavior, what I'd like also to tell you a little bit at the end of the presentation. But let's start with the classical material characterization. The classical material characterization, as we all know, in the field of material characterization of polymers includes tension, compression tests, creep, relaxation, dynamic mechanical characterization. We can characterize multi-axial loading. We can characterize multi-axial contacts with different tribological systems and with interaction between adhesion, deformation, and all different materials and multi-layer buildups. When we think of elastomers in this field of application, a very simple example, compression tension, then you see here in the first step the compression and tension curve of an HMBR, and you see here the strong nonlinear behavior and the difference between the compression and tension behavior of the material. What you also can see here is that we've applied or we've implemented these tests at different temperatures, 79 to 110 for compression as well for tension. And what we see here is that the influence or the impact of this test temperature, 79 and 110, is not really that big on these test results. The only difference what we can see here is that we have a little bit of a decrease in the stress and strain at break when we increase the temperature. Additionally, when we're thinking of tensile testing and also of rubbers, then we always have some fillers inside of the material. And therefore, we'd like, with this topic or with this study, what we've implemented, to analyze a little bit more the impact of processing imperfections and also the impact of different filler sizes. And therefore, we introduced to the material different sizes of gas beads. So we used small gas beads, large gas beads, and we also used it in an untreated and untreated way. And what we received here was also that with the larger beads, based on specimen geometry on a S2 specimen, based on the DIN 53504, we've seen that we have from the pure HMBR to the large beads nearly the same material behavior. But when you introduce the small beads, we found a clear decrease of the stress and strain at break. We used also here a different, not a different, material field with 0.5 weight%. This means that we had much more smaller beads in compared to the larger beads, which explains also this behavior here. And what we then finally also found was that with the untreated and treated way, just to give you an idea and to show you the influence of this treatment, that with this untreated material of these small gas beads, we found a lower stress and strain break. Additionally to the tests, we've also implemented some micro CT measurements with another K1 center in Leoben, the material center. And you see here red dots the bigger gas beads and then the smaller gas beads. And we also looked directly to the gas beads, where you can see here for scanning or the results for scanning electron microscopy. When we now think of classical tensile testing, then nowadays also more and more smart materials came up for different applications. And what is already applied for different composite materials to receive this load coupling, for example, for some wind aero plates, or to have this aeroelastic tailored applications. We've also tried to implement for soft materials, which means that we replace the resin with the silicon and tried to introduce some load coupling mechanism directly in soft materials to combine both, for example, distinctive tension twist coupling. And therefore, we developed also different test setups. Here, an example, we developed the test chain starting from single fiber tests, where we've used single fibers or the characterization of single fibers, where we work together with some scientific partners. Then we developed here in Leoben a test setup to test some fiber bundle test setups. And finally, we've implemented also some test setup where we directly started or ended up with the possibility to test directly a woven fabric. And as you see here, for different materials, the left side for silicone polyurethane with glass fiber, and on the right side for the matrix material, silicone polyurethane with polyester fiber, we see that we have here the normalized pull-out force, and we've received for the fiber bundle test, for the woven fabric test, and for the single fiber test, at least the same tendency, the same trend, which ends up that we can characterize much more easily with the fiber bundle and a little bit more application oriented compared to the single fiber test. However, focusing on the woven fabric, we've implemented tests here, first of all, with setups where we've only have 1 and 2 layered systems, where we characterized some different fiber orientations. For example, here you see the fiber orientation 0-90 degrees, where we received a very stiff material performance compared to ±45 degrees, where we have a much higher strain or a much larger strain compared to the lower stress when we compare it to the 0-90 degrees. And what we found here was also so-called wrinkling of the material. You see it here also with this trellis effect. This is based on the shear principle. because when you reach this maximum shear angle, then also no in-plane deformation is possible anymore. And therefore, you ended up with this wrinkling, and finally with the break of this setup or of the material. Okay. Switching from classical testing a little bit more to material modeling, when we think of classical material modeling, then we need some material data as input parameters for our simulation routines. In a very simple, very easy way, we need uniaxial material data, we need biaxial material data, and we need pure shear material data in a very simple way. When we think of elastomers, then we think of hyperelastic material models, also very simple at the beginning. And here we have to define strain energy density. And this is a specialty of elastomers and of soft materials, that we have a hyperelastic material performance, which the performance of the material is based on an energy compared to classical polymers. This means when we just think of different material laws with different hyperelastic material laws, which are already implemented in some simulation tools, for example, Abacus, where you can choose out from a Neo-Hook model to Mooney-Rivlin model to Ogden model, only to give you an example. However, these are all just basic models which explain a hyperelastic material law. Nevertheless, you always have to think of where are the limits of your application and for what you'd like to do your simulation. These are two very important points because, for example, the Neo-Hook model fits well uniaxial tension experience up to a maximum deformation of 40%. This means when we have an application where our material is applied up to 500% deformation, then the Neo-Hook model will not fit very well. Therefore, there are also a definition of other models like the Ogden model or the Mooney-Rivlin model. However, as I mentioned, these are really the basic material models. And what we're also doing here is to develop new material models, especially also for composite materials. And one aim we are focusing on here is, for example, to develop homogenized material models to describe the hyperelastic material behavior. And only to give you an example or a very quick overview, for example, here we have the MFI model. This MFI model describes the matrix behavior, describes the fiber behavior, and additionally, when we think of our material, what I've showed you before, showing this wrinkling effect, then we also have to explain these matrix fiber interactions. And here our simulation group has introduced a new matrix fiber interaction and also a new invariant, explaining these material behavior as you see it here. And here you see two examples, one for plus minus 45 and one for plus 30 minus 60. And as you see also here in those two results, the experiment indicated by the green dots fits very well the MFI model, what we've developed here for this plus minus 45 as well as plus 30 minus 60. Additionally, you see also that the surface strain, what we directly measured with the camera system for these two setups. However, from these simple tests or for the simple material model, we always want to go to an application, as I also introduced at the beginning. And therefore, we also want to describe the load coupling behavior with a composite layup. And here, we've just introduced some simulation tools. We have adapted this model and more or less with the aim to introduce defined end twist or defined end moment when we apply a defined force to the material. Ending up with a lot of dots when we think of a moment as a function of the end twist, where we see more or less where we can achieve the highest or the biggest load coupling potential based on our material model what we developed, and also based on the theoretical observations what we have made so far. Here, we are still on a theoretical way, and to bring this to reality, we also have to measure this end twist. We have to measure this moment, what we can receive with our different layers. And therefore, we've designed the concept, or we've defined the design concept to measure this load coupling forces and moments by introducing a new load coupling test setup, directly recording the twist angle, the torsion force, and the tension force. And here we are with the first results of this test setup. On the left side, you see stress-strain properties. On the right side, you see the twist angle. And what you can see very clear is that we've monitored the stress depending on the strain for plus minus 45, 30-60, and 30-60 plus minus 45. So all of these are two-layer buildups, which means 2 layers of plus minus 45, 2 layers of 30-60, and here we have 1 layer 30-60, 1 layer plus minus 45. You see here clear the different material behavior. Additionally, we've also implemented a study with different clamping distances or Gaussian lengths. And you also see here that for the twist angle for plus minus 45, we received nearly nothing, whereas for 30-60, we received twist angle of up to 25%. The colored pictures, what you also see here, are not simulation results. These colorful pictures are directly measured. It's the measurement of the surface strain with a camera system. And actually, we are in the phase of directly correlating these simulation results with our test results to verify also this test setup. Good. Now, when we're leaving the material models, we're going in the direction a little bit of aging of the material. And aging of the material, when we think back to different applications, doesn't matter if oil and gas, space, some industry applications, we have always some media, we have always some temperature, we have always some harsh environments, which are directly reducing the lifetime of our materials or impacting the lifetime of our materials. And here we are talking about when we apply it to higher temperatures, about thermo-oxidative aging. When we have some oil, some swelling agents, then the material will swell. And for sure, when we have both, so media and temperature, then we have a combination of both effects, which leads up to more or less high impact of thermo-oxidative aging or swelling. As an example, you see here an impact on the loss factor. So based on the dynamic characterization, we've defined storage modulus, loss modulus, dynamic modulus, and loss factor. The loss factor tangent delta also represents the damping of the material behavior. And we've studied here the material performance. So in this case, one more time about HMBR, black line virgin. Then you'll see red, blue, and green line aged with 100 degrees, 24 hours, 72, and 168 hours. And then we've just increased the temperature. So from 100 to 150 to 170. Whereas at 100 degree C, with 24 hours, 72 hours, and 168 hours, we see not that much impact. With 150, the impact already starts. So the black and red curve are nearly at the same, but the blue and the green curve are already going down, which means on one hand side that the damping of the material changes, And on the other hand side, when you also look at the maximum, what we see here for the loss factor, that also the gas transition temperature is shifted to higher temperatures. And with 170, we see this even more pronounced with already with 24 hours at 170, we see here a strong difference between to the virgin material behavior, what we found for HMBR. But we see this not only in our dynamic mechanical characterization, what is representing the network, or more or less the damping capabilities of the material. We see it also, for example, in stress strain curves. When you think here I've just showed you, or I'm showing you just 3 examples. So maximum aging time, always the same with 168 hours, applied to 100, 150, and 170 degrees C. And what we've seen here is the virgin curve ending up with a strong increase of the stiffness, a clear decreasing strain, and a strong decreasing stress. And this just with 168 hours for an HMBR, which is usually applied for high temperature applications. Leaving the aging of the material, we will come to material fracture and to the fatigue. And when we're focusing material fracture and to the fatigue testing, then we can also think of a lot of different applications where these play an important role. When we have different frequencies, when we, for example, think of hoses in different machines, when we start the machines, then we have some frequencies up to kilohertz, which are going through the material and sometimes fail or leads to failure of the component. We also have a strong influence of different temperature. When we stay with machines and the hoses, then we also have most times some heated oil inside these hoses or some hydraulic fluid, which also leads to an impact of temperature and for sure with an impact of this loading amplitude. And here, I'd like to give you a short overview and like to introduce, or more or less to explain a little bit more about the fatigue. What is fatigue? So basically, fatigue describes the weakening of the material caused by repeatedly applied loads and so-called cyclic loading. This means more or less just apply a cyclic load to our material. And here we can distinguish between 2 approaches. So we have the crack nucleation approach, which is more or less based on sample specimens, and a Reuleaux approach. This means I've defined stress amplitude. This stress amplitude I'm applying to my sample specimen, and then I'm ending up with a number of cycles to failure. Second approach is the crack growth approach. More or less, it's the more fracture mechanics approach based on a tearing energy, explained by a Paris-Erdogan approach or Paris-Erdogan plot, and using, for example, in this case, some pure shear specimens. For today, I'd like to focus a little bit more about the crack growth approach. I'd like to give you an insight of what we've done here so far and what we have developed. You see here our test setup in the lab, where we have our specimen with IR sensor, a crack detection system, so a camera, to finally monitor our crack growth over the number of cycles to failure or the number of cycles to load. We developed a method where we can measure directly with this camera crack tip position, X, Y, and then finally end up with the contour length to finally calculate then fracture mechanic parameters. These fracture mechanic parameters, in this case, we've chosen the tearing energy for pure shear specimens. And more or less the important thing for us is, on one hand side, the hysteresis, which means the area under the load, displacement curve. And on the other hand side, the uncracked specimen area. Therefore, we need the position of the crack. With some boundaries, ending up definition of the strain energy, as I mentioned. So we have the total energy, with dissipated stored energy. We defined in our case minimum energy, and then ending up with this encracked specimen area, as I mentioned before. This brings us also then to the results. And here we also have one more time a lot of different influencing factors, as I mentioned before. The first case, the parameters effect, we've measured with this camera system, for example, for different frequencies. So we've implemented these tests for 0.25, 1, 4, and 10 Hertz. And as you can see here in our results, for higher frequencies, we received a lower crack growth rate. In the first, or when you think of this in the first way, then it's a little bit weird or a little bit strange. But we've searched a little bit the literature and also think a little bit more into detail about this. And at the end, it makes sense because the crack growth rate, the total crack growth rate, consists of a static part and a dynamic part. And here, when we increase this frequency, the static part will decrease and the dynamic part will increase. And therefore, due to this decrease of the static part, the crack growth rate total is a little bit lower compared to the lower frequencies. We have a load ratio effect, which means minimum stress compared to maximum stress, so divided by maximum stress. So load ratio R of 0, 0.3, 0.5. And we see, or we've observed also here, a small increase or a small impact with these different load ratios. And finally, ending up where we always end up with the effect of temperature, clear difference of 25 degrees C, 40, 60, 80. And please keep in mind that we have here a log scale, which means that here from, for example, 25 or 40 degrees C to 80 are 2 decades, which means there's a big difference in this scale. Staying with the temperature, we also looked a little bit more into detail because when we talk about application time in terms of fatigue, in terms of hysteretic performance of the material, then temperature always plays an important role. And therefore, we've applied also an IR camera. And what you can see here is the surface temperature as a function of the number of cycles for the different frequencies. As I showed you before, for 0.25, 1, 4, and 10. And as you see it here, for 22 to 24 for the lowest frequency, but we are here from roughly 24 up to nearly 30 or 10 Hertz. At the end, this is only for a pure shear specimen, and the pure shear specimen just is a little bit from the thickness much lower than compared to the Dumbo specimen, which means that Dumbo specimen, the roughly diameter of 12 millimeter. Here we have a thickness of 4 millimeter or 6 millimeter, which makes a big difference. Additionally, not only the specimen geometry has a big impact, also the material performance has a big impact, which means that for material A, for example, here we have nearly a linear behavior or more or less a linear behavior when we're talking about elastomers, whereas with material B, with a strong non-linear material behavior with high deformations, which ending up to much higher temperatures. When we think of 1 and 4 Hertz of Dumbo specimens in this case, we're ending up in the comparison from 1 to 4 Hertz, nearly up to 100 degrees, which is a huge impact of temperature on our material when we think of the impact that we've seen before on thermo-oxidative aging for HMBR. Additionally, we also measured the internal temperature of such Dumbo specimens. So we directly molded the thermocouple inside of this material, and we've done this several times to get a little bit of an average what's happening, and what we've seen that also what we've expected, that the core temperature is even higher compared to the surface temperature, what we've measured outside of the material. And this brings us more or less to the next point, to complex loading behaviors, where we are more or less back to oil and gas industry, where we have very complex loadings and also very harsh environments, as I showed you in the introduction. For example, here this hose failed at 1,300 bars, and nobody wants to have this burning oil rig onshore, offshore, wherever. And here we also cut a hose open where you can directly see some blistering and also some cracks inside of the material. To describe this very complex loading, we've also, or one more time, like to give an overview of these applications, just to bring it back into mind. Safety applications like blowout preventer, different hoses, Christmas trees. And what we have done so far is that we've also focused here on the rapid gas decompression behavior. So very special behavior, especially for materials which are applied to high pressure gases. So nowadays, this is for sure very important for oil and gas industry, but there is also a very important second application where we'll focus on in the last slides. And what we can see here is at the beginning, we have always a compression phase, which means that we apply temperature and the pressure, in this case up to 150 bars. This means to increase of the material due to the penetration of the gas inside the material. And then when we just have to more or less disturb this equilibrium state, our decompression phase starts, where we have some temperature fluctuations at the beginning and at the end. And with this decompression phase, the stored gas inside of the material leads to an even higher volume change, and then finally to a cracking of the material. So in this case, blistering, crack initiation, crack growth, and then finally the failure. One testing standard, or two testing standards is NACE and NOSO testing standards. They explained temperatures, pressures, specimen geometries, also gases for gas industry, in this case, the CO2, CH4. And then more or less you're storing your O-rings directly in the autoclave, testing it concerning to the testing standard, and then you are rating the cross-section after the tests of your O-rings, which means that you cut your O-rings, what you get out of the autoclave into 4 pieces. Then you use a microscope or a camera, just make pictures of this cross-section, and then you're counting what's happening and how much cracks you can measure and how long are the cracks. And then you have a rating from 0 to 5, where 0 means no cracks, so very good, and 5 means completely separation of the seal into fragments, which means completely failed. What we have done in this case, or so far, is that based on the testing standard, we can just observe the material behavior after the test in terms of fracture. And we'd like to go here a little bit more into detail. Therefore, we developed together with a company partner test setup, so an autoclave test system with a camera system, where we can directly measure the volume change during the compression phase as well as during the decompression phase. You can see the autoclave temperature unit, the pressure, here in this case, 272 bars. And what we've measured are, in this case, one more time, the compression phase, the decompression phase, and additionally to the pressure and temperature, what we directly monitor over our equipment. We can use also the volume increase during compression phase, the volume increase during decompression phase, and then we can also define some additional parameters, for example, like an initial time, which is needed until the volume increase starts. And here I've brought with me a sample of 2 different fillers. So basically, more or less, the material is the same, just used filler A and filler B. And what we can see here now, the decompression phase starts, clear volume increase for both, but for one sample, the material cannot withstand this crack initiation process leading to a rapid crack growth inside the material, and therefore you have like a rocket effect where the crack or the gas which is stored inside the material spontaneously is released by a crack, and the second material was very good performing with a ranking of 0. However, when you think a little bit more into detail, a little bit more closer about this, then I've brought you a little bit examples with me of virgin material, of an aged one, thinking of the impact of time oxidative aging. And then also additionally here, we have brought with us, or I've brought with me a swollen result, where we've swollen our samples with an IRM9 of 3 at 100 degrees for 168 hours. Result of volume increase during compression phase and during decompression. What we found so far is for virgin one, roughly 10% during compression, 40% during decompression. For the aged one, we have also 10% during volume increase during compression, 30 to 35% during decompression. And for the swollen one, we've observed lower volume increase during compression and also a much lower decrease during decompression. Also, these results look in the first way a little bit weird, but when you think a little bit closer about what's happening in the material, then, for example, for the swollen material, we've observed a lower volume increase. This is more or less clear because we've already liquid inside of the material. This means that there is not a big capability of storing gas inside the material because our material is already swollen. When you think of our aged material from 40 to 32% volume increase, it's also clear because when you think back on the impact of thermo-oxidative aging, we've found a stiffness increase, a decrease of stress, a decrease of strain break. And this increase in stiffness leads to a lower volume increase because this means that the material fails earlier, breaks faster, and therefore it cannot expand like a virgin one. And even more or less volume change of the swollen one, because the same reason like here we have less gas inside due to the fact that we've already some oil inside of our material. However, so far so clear, explained, and looks good. So based on this explanation, it should be that the virgin one showed the best material performance. When we think now of what the material finally performed, is that the virgin one showed the worst performance and the best performance were showed by the aged one. This is also one more time due to this increased stiffness. And this should show you also that the material behavior is not that easy to correlate. And we should always consider different influencing factors. And in this case, the aged material performance was the best one because of these higher crosslinks, because of the stiffer material performance. However, when we increase the pressure from 150 bars in this experiment up to 200, 300, 400 bars, then it would be in another way and the ranking would also be different. And as I told you also before, this high gas application is not only for oil and gas industry. When we think of future energies and also of the field of application of hydrogen, then we also have the same situation for hydrogen gas, which means that we have gas storage up to 1000 bar with a temperature -40 to +85. In the fuel cell vehicle, we have the gas storage up to 700 bars, -40 to 85. We have a fuel cell stack. We have different materials all over this hydrogen production, fuel station, fuel cell vehicle, and fuel cell stack, which means that we have, for example, polyethylene, polyamide, we have rubbers, we have different high performance materials like PEEK, and all these different materials are exposed to these extreme operating conditions and are more or less influenced by these gases' temperatures. And also, just to give you an insight here a little bit, with, as I mentioned at the beginning, at the introduction, also leading the project called Polymers for Hydrogen. We're exactly focusing also on that field. And this project has 3 smaller projects included, which deals project 1 with storage of high pressure gas, where we're going in the field of design and development of novel multi-layer buildups and the scientific basis for line of 3 type 5 high pressure storage tanks. Then also very important, the characterization of the permeation and the buildup of a robust permeation test setup, which will be focused on the transport of high pressure gas. And then also in the 3rd project, which is a little bit more into complex material behavior, rapid gas decompression and tailoring filler matrix interface to withstand these extreme operating conditions, environments and fluctuations. Good. And more or less, this brings us also back to the slides, what we've seen before, why we are doing this and what is the main goal of this. So we are trying to setting up this classical testing, combining with material modeling, chemistry, aging of the material, swelling, with special characterization methods, finally to enhance the component understanding, to understand what's happening in the application, to increase the material reliability, and finally to unlock new application fields and assist new applications. Then I've brought also with me the scientific basis of the presentation. So our latest publications, what we have so far in our research groups. And finally, I've also like to thank all scientific partners, all company partners, and also the PCCL for financing more or less this research. And thank you very much for your attention.
Oh, thank you very much, Bernd. What I forgot to tell in the beginning is there is the possibility to ask questions via the Q&A, the comment function. So if you haven't done it yet, please just type in your questions and we will answer as many as possible in the next minutes. Before we start with the question, I also want to point out the next webinar will be in March, exactly on March 9th. It's again a Tuesday on 2 p.m. Central European time. And our colleague Sandra Schlögl will tell her results on self-healing of polymers. So maybe to start with, Bernd, I have a question. You showed that when the elastomers, the rubbers age, then the damping behavior goes down and usually the shore hardness goes up. Did you observe in any case like depolymerization or let's say massive transition of the elastomers after some time?
More or less what we observed so far is that for our elastomers, what we've focused on, so basically were HNBR, NBR, and also some BRs, that when you start to age the material, then you have just starting also radical chain formation because you're breaking the chains, and this change breakage leads to the radical formation and then to the further degradation of the material chains, which ends up with a stiffening of the material until you finally end up with a very, very stiff material, and with a material which then performs nearly like a coal, ending up finally. So it will be stiffer and stiffer, and the capability of strain will be less and less what the material can perform. But at the end, it will be always some compact, and of more or less the elasticity of the material will be lost completely.
Okay, then we have the first question from the audience. Do you have any results concerning hydrogen diffusion through different polymers?
We are actually working on the field that we are setting up our permeation setup, and our permeation setup will be, or more or less it will be possible to measure the permeation of the materials up to 1000 bar. But this setup is just now in the conception phase, and we've ordered now more or less the first things for the setup, especially also to measure the permeation through the material. And here we're looking forward to receive first results in summer this year.
Okay, so there are no more questions from the audience. With that, Bernd, thank you very much for this very interesting talk. Most probably we will be posting the video of this webinar on our YouTube channel in the next weeks. So if you want to have another look or maybe send it to your colleagues, this should be possible in a few days, and we will of course send out a notification on this. So with that, thank you very much again, Bernd. Thank you also to all of you for listening to our first webinar, and we are looking forward to seeing you again in 2 months at our second webinar on self-healing of polymers. So have a nice day.
Thank you very much. Bye-bye.